Okay, so we're going to go through our two examples for Taylor polynomials. We're going to do one for f of x equals ln of x. We're going to center it at a equals 1. We can't center this one at 0 because this function doesn't exist at 0. So here's a case where we can't even do a Maclaurin polynomial. We can only do a Taylor. We're going to go up to the 4th degree, which means we have to go up to 4 derivatives. So I like to keep this table of our function, ln of x. First derivative is 1 over x. Second derivative, using your power rule, is negative 1 over x squared. Third derivative is 2 over x to the third. And then our fourth derivative is negative 6 over x to the fourth. And we're going to evaluate all these derivatives at the center, which in our case is 1. So we plug 1 in, we get 0. We get 1. Plug 1 in here, we get negative 1. Plug in 1 here, we get positive 2. And if we plug in 1 here, we get negative 6. So when we plug it into our formula for Taylor polynomials, our 4th degree polynomial, I like to use this subnotation for 4, is 0. It's our constant, plus first derivative over 1 factorial, x minus 1 to the 1. And then our second derivative over 2 factorial, x minus 1 to the 2. Our third derivative value over 3 factorial, x minus 1 to the 3. And our fourth derivative over 4 factorial, x minus 1 to the 4th. And this will simplify nicely and give you a nice pattern. If you wanted to continue this to find the 5th degree or the 6th degree or the 7th degree Taylor polynomial, we could easily do that now without having to continue our table because we can identify our pattern. So what this is saying is that this polynomial, this 4th degree polynomial, can represent this function, f of x equals ln of x, but not necessarily everywhere. When we talk about intervals of convergence, an interval of convergence is when this function, this polynomial, can model this function. So even if we did go to an infinite number of terms, we're still only going to represent it over a certain interval of convergence centered around x equals 1. Okay, so now for our second example, we're going to do a 6th degree, which sounds like a lot, but you're going to see that it's not going to be as much. Maclaurin polynomial, so that means the center will be at 0 for our function f of x equals cosine x. So we have to go up to 6 derivatives, but that's pretty easy to find here with cosine. So we start with our value of our function, first derivative, second derivative is negative cosine x, third derivative is positive sine x, fourth derivative is cosine x, fifth derivative is negative sine x, and sixth derivative is negative cosine x. So now that we have all those derivatives, we're going to evaluate all of them at 0. So our function at 0 is 1, then our first derivative is 0, second derivative is negative 1, third derivative is 0, fourth derivative is positive 1, fifth derivative is 0, and sixth derivative is negative 1. So these derivatives were pretty easy to find and to evaluate. When we list out all of our terms, we notice that every other term has a 0 in the numerator. So those terms are just going to be 0 altogether. So we don't actually have to put them in our final answer. So when we simplify this 6th degree Maclaurin polynomial, we actually get just 4 non-zero terms. All right. 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th. And we should easily identify a pattern, and we can then find the series that would represent cosine of x. Again, this polynomial will represent cosine of x, but only on some interval of convergence. That could be a finite interval. It could be infinite. It could just be at the center. That's what we've talked about in 8.8 and 8.9. We could also use this series now to do certain things. So it says to use the first 3 non-zero terms. So that doesn't mean 3rd degree. It means first 3 non-zero terms to approximate cosine of 0.1. So we're going to take these first 3 terms and just replace x with 0.1. And that would give us this approximation. We don't actually have to evaluate it. We can just leave it in this form. 1 minus 1/2 times 1/10 squared. There should be a squared right here. Sorry, that was my mistake. So it should be 1 over 100 plus 1 over 24 times 1 over 10,000, because that's the 4th power. And then when it asks about the error bound, since this is an alternating series, the biggest error has to be less than the first missing term. Therefore, our error has to be less than 1 over 6 factorial x to the 6th, and we can replace x with the 1 over 10. So 1/10 to the 6th would be 1 over 1 million times 1 over 720. Right? And the sign is irrelevant because we're doing absolute value. All right, hope this helps, and I will check your answer to your AP question today.